In previous videos, we have analyzed centrality metrics and position metrics. And now we're going to talk about dispersion metrics. Dispersion metrics are relevant when we're trying to capture how widespread are our observations, when you want to check like how precise it's the data. Remember the discussion about accuracy, which is related to the centrality measures, and precision. So precision is related to dispersion. So variation in general can be observed in many processes. For example, a machine that is used to fill a bag of rice, even though you set the machine to, let's say, to fill the bag up to 1 pound of rice or 1 kilogram of rice, if you start weighting those bags, the final product, you will notice that the weight of each product is not exactly the same. Why? Because there is some variability in the machine, and that's normal, because in every single process in nature, you don't get exactly the same result. There are some different sources of variation. For example, there are some human factors. So if the person that operates the machine is different, so maybe the performance different of the machine. Some of the raw materials, if they come from these different suppliers, so it is expected that the performance or the final result is not exactly the same always. So again, in different processes, the outcome in general will have some variability and some dispersion. The purpose when you study statistics and you're an engineer is that in any process that you manage, you want to minimize or reduce the uncertainty, the dispersion, because a dispersion is a synonym of uncertainty. So the more dispersion you have, the more uncertainty you will experience when you're making decisions. So the smaller the dispersion, the better in general. All right, so now let's learn some metrics to capture that dispersion. The first one is going to be the range. The range, it's a very general metric, and it measures the distance between the minimum value and the maximum value in a data set. In this example, mind that we're trying to assess how good students are doing in a quiz. So we're comparing two quizzes, quiz 1 and quiz 2. But now we want to check like the dispersion of the data. So we want to know if the students the precision or the variability was low, or if the dispersion was high. So using the range, so we take the maximum value, number of correct answers is 5, and the minimum number of correct answers it's 1, right? Then the range for the first quiz, it was equal to 4. Now if we do the same for the second quiz, the maximum value, please notice that there are some observations here, like 4 observations or 4 students that got 5 right answers, and there is only 1 that got 1 correct answer. So again, the range for the second quiz is also 4. So the range is the same for both of the data sets. But if you start looking at the data, you will see that, for example, for quiz 1, please notice that most of the observations are clustered here in 4 and 5, and there is only 1 observation here. But now if we check the second quiz, we can see that the observations are like spread like uniformly. So that means that the dispersion is higher in this second quiz. However, the range is not capturing that. It's not capturing that dispersion. So that means that the range is somehow limited when we are measuring and comparing dispersion in different data sets. So let's add another metric into our tools. This is the variance. This is one of the most popular variation metrics or dispersion metrics. The variance measures how widespread it's our data, and the idea is that we compute the distance between each observation of the data set minus the mean value. So this is the distance, the difference. We square that value, and then we add those square differences, and then we average them. So we divide over the number of observations. Here we have two equations because one is for the parameter. This is population variance. The population variance, that's sigma square, and A square represents the sample variance. Now, there is only one big difference in addition to the notation. Please notice that in the population variance we divide over the number of observations, while in the sample variance we divide over n minus 1. So the sample size minus 1. So some facts about the variance. First, it captures variability, it measures dispersion. So the higher the variance, that means that the higher is the variability or the dispersion in your data. The higher is the uncertainty. Now, one of the limitations of the variance is that it is expressed in square units. Because if you check the equation, there is a square here. So the units that you get are squares, so are different than the original units of the data set. So that's one of the main issues, because the interpretability gets affected by this fact. Now, if we have two different data sets and we compute the variance for each data set, we cannot compare them. We cannot compare them because each data set might be in a different scale or different units, so the variances cannot be compared that easily. So be careful. There are alternative ways to compute the variance. So this is one of the possibilities. This is a second equation. So you can use either equation you want. This one, which is the one that you will find in every single textbook, right? The sum of the distance between each observation, the means, that value squared, sum divided over n, or this second expression. The only difference here is we just have the sum, not of the difference, just the sum of xi squared, and then to that result you deduct n times x bar squared. So either way you should get the same result. So instead of sample variance, you want to find population variance, you change the notation. So instead of s you will use mu, and instead of n minus 1 you will divide over n, right? Same thing as in the previous equation. So let's keep using the same example. That was the motivation of this video. We're trying to compare these two data sets. So quiz 1 and quiz 2. Quiz 1, quiz 2, or set 1, set 2, same thing. So our hypothesis is that quiz 2 has higher variance or higher dispersion, right? So let's check that. The range was not a good metric to compare them. Let's see if the variance work. So if you check this data set 1 and set 2, they have some observations with frequency different than 1. So for example, observation 1 has a frequency equal to 1, but the number 4, the outcome equal to 4, it has 3 observations with the same value. So frequency is equal to 3, and similar thing happens with the 5. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 observations equal to 5. So we can use that fact, we can use that structure in our data. It's like similar to translating the dataset into a table, a frequency table, where you have the x value, that's the outcome, so it will be like 1, 4, and 5, and you have the frequencies, so it will be like 1, 3, and 9. So why is that useful? Because, for example, when you're going to compute the x bar, instead of adding every single value, 1 plus 4 plus 4 plus 4 plus 5, 5, 5 plus 5, 5, 5 until the last one, and then divide the whole thing over the number of observations. So it's better to just multiply each outcome of the variable times the frequency. So 1 times 1, 4, the value of 4 times 3. 4 times 3 is the same as 4 plus 4 plus 4. It's the same thing, right? Or 5 times 9 is the same as 5 plus 5 plus 5 plus 5. So you've noticed these equations right here, they have a slight change here. So we're adding the frequency. The frequency is the sum, the frequency times the value of the variable. So using the on-group frequency table, you will be able to use these equations. So again, you can use the original equation for the mean, or use this equation where we're implementing the frequencies, the absolute frequencies. At the end, you will get exactly the same result. But I think this one is going to be faster, right? Because we have some repeated observations. So if we can do that for the sample mean, same thing applies for the variance. So in the variance, remember that we have two equations, equation 1 and equation 2. So now, since we have some observations that they repeat several times, so instead of just doing the difference for every single observation, it's better to do it for each outcome of the variable, for each possibility, and then we multiply that square difference times the frequency. So it's gonna save us some time. But again, this is optional. I think it's the fastest way to solve this problem, but it's optional. So if you wanna get the original equation, that's fine. But if you wanna like use the property of the frequency here, it's gonna make your life easier. Okay, so for the first data set, we can arrange now in the table as I just did in the previous slide. We can compute what we need to get the sample variance. So we find the x bar, it's equal to 4.46. And for the variance, using this alternative equation, the second one, we get that the variance is 1.27. So that's the value that we want to compare. We want to check this variance and see how's the variance or the dispersion of data set 2. So we arrange our observations of set 2 in a table for this set. It's a little bit longer because we have more outcomes here. 1, 2, 3, 4, 5. That's why we have 5 classes, right? 5 classes, that's K. And X represents the value of the outcome. 1, 2, 3, 4, and 5. In this case, they match the numbers, but that's not always the case. We get the frequencies. So there are, for example, the outcome equal to 4. There are 2 4s, right? These 2 4s. So once we have all the information, then it's easy to compute x bar and the variance. So in this case, the variance is 2.8. So if we go back and we compare with set 1, please notice that variance was 1.27, and here again it's 2.08. So the variance in the second set is higher. Now, when we were discussing some of the properties of the variance, we said be careful when you're comparing variances because they may be in a different scale. But in this example, set 1 and set 2, these are correct answers, and in both cases, the values are from 1 to 5. So they are on the same scale. They are not that different. Therefore, it makes sense to perform a comparison here. So we can claim that set 2 has higher variability because the variance is higher. There is higher dispersion compared to set 1. And that kind of like confirms our hypothesis, right? And our hypothesis was that the dispersion in Q2 was higher than in Q1. Okay, so as we said earlier, one of the limitations of the variance is that we will have square units. So to kind of like to try to solve that issue, we have a metric called the standard deviation. What the standard deviation does is that it applies the square root to the variance. In that way, you get a dispersion metric that is in the same units as the original variable. So you don't have those square units anymore. So this is an alternative metric. It's popular too, the standard deviation. And lastly, we have the coefficient of variation. The coefficient of variation, or the CV, is a way to measure variability. But the nice property of the CV is that it doesn't have units. It's dimensionless, unitless. So the equation is equal to sigma over x over mu. This is over mu, or S over x bar. That's let me fix it a little bit here. So it's S over x bar, right? This is for population and this one is for sample. Why the CV is nice? Again, as I said, it doesn't have units because they cancel out. The units of S are the same units of X bar, or the units of sigma are the same units of mu. So when you divide one over the other, then you will cancel the units. So that's nice because then you will be able to compare the dispersion of two different data sets. So let's check an example. So a company is providing the sales of item 1 and item 2. These are two different products. So now we want to compare the variability of these two products. So let's compute the different metrics. So we can find X bar for both metrics. So for the first one, X bar, you know how to find X bar. It's going to be 5 plus 7 plus up to the last value 8 divided by the number of observations. That's 1, 2, 3, 4, 5, 6 number of observations. Same idea for item 2. So X bar, this is for item 1, this is for item 2. Then X bar, I will give you the numbers right away, 7.17 and 20.5. That makes sense because if you notice these numbers are higher than these numbers, so it makes sense that the mean of the sales of item 2 are higher than the mean of the sales of item 1. Okay, but now if we find the standard deviation, that's going to be 2.23 for the first item, and for the second item it's going to be equal to 2.88. Now someone might claim that the standard deviation is higher for the second item because the 2.88 is higher than 2.23. But the problem is not that simple because if you check the X bar, they are way different. So I2, the item 2, it's on a different scale. It's on a different scale. Numbers are way higher compared to the numbers of I1. So it's not that simple when you compare the standard deviations. So if you want to get rid of the units and make a fair comparison, you need the CV. Remember, CV is the standard deviation divided over the X bar. So if we do that, then we get that the CV for item 1 is 0.32, and the standard, the coefficient of variation for item 2, it's 0.14. This is like the percentage of the dispersion. This is the percentage of the standard deviation using as a reference using the mean as a reference. So if you notice, the coefficient of variation is higher for item 1 compared to item 2. That means that the variability or the dispersion is higher in the first data set. So even though the standard deviation is lower here, when you compute the CV, which is a relationship between S and X bar, we can notice that the dispersion is way higher, almost twice. It's more than twice the coefficient of variation in the item 2. So this is a better metric to compare dispersion in two data sets. All right, so just to summarize, in this video, we discussed some dispersion metrics, the range, the variance, the standard deviation, and the coefficient of variation. I'll see you in the next video.